Welcome again to Flipped Harbor for Calculus. In this video we're going to talk about two methods for taking the derivative called the product rule and the quotient rule. Our objectives for this video are to learn how to apply the product rule when taking the derivative and how to apply the quotient rule when taking the derivative. Our outline for this video, we'll talk about what the product rule is. We'll look at it in rule form. And I'm going to demonstrate the product rule compared with taking a derivative without the product rule. And I'm going to kind of use that as a proof of the product rule. It's not a real proof, but I'm just showing you that yes, this does work. Then we'll take a look at another example of applying the product rule. Then we'll move on and take a look at the quotient rule, and I'll try to teach you a fancy way of remembering it. And then again, we'll take a look at a quote-unquote proof of the quotient rule, and then we'll end with an example to apply the quotient rule. So the product rule is a rule that we use when we have two or more expressions that are multiplied together. So if I want to take the derivative of f of x times g of x. So we're looking at two algebraic expressions that are multiplied together. They may be big polynomials that are multiplied together, or it could just be a couple little expressions, maybe an exponential e to the x times a square root. It doesn't necessarily have to be big expressions, but when they're multiplied together, we've got to use this rule. So to take the derivative of this product, we take the derivative of the first expression, just the derivative of the first expression here. This is just f primed of x times g of x. So what that means is we take the derivative of the first part, but not the second part. And then we add the derivative of the second part times the first part. Now that's the original first expression, not the derivative of it. So notice what has the prime on it, what has the derivative on it, and what does not. Now the product rule, we generally can't hurt too bad if we get some of these things mixed up, because multiplication is commutative, because addition is commutative. It's a little bit harder to mess this rule up. But try to stay in a pattern so that once you get used to that pattern, you kind of flow through it very easily. Now, if we want to take the derivative of something that has more expressions multiplied together, so here I have the derivative of f times g times h, so we have three expressions multiplied together. Basically what you do is you take the derivative of one expression at a time and multiply it by the original expressions. So this pattern works with 3 or 4 or 5 or 20 expressions multiplied together. You take the derivative of each little piece separately and you multiply it by all of the other expressions, all of the other original expressions. So you see I have f primed times g times h plus, it's always plus, and then I take the derivative of the second expression, g primed times the original f times h, and then h primed, the derivative of that third expression, times the original f times the original g. And then we can continue this pattern on out forever. Okay, so let's take a look at a quote-unquote proof of the product rule. Not a technical proof. I'm just trying to show that yes, this works. So what we're going to see is I'm going to take the derivative of this product, 3x squared plus 2x times x squared minus 8. And I'm going to do the algebra first. I can FOIL this out and avoid the product rule. And then we're going to take a look at using the product rule and then ending with some algebra. And what you're going to see is we get the same answer either way. So the first thing I need to do, if I'm going to do the algebra first method, is I need to go ahead and FOIL it. 3x squared times x squared, 2x times x squared, 3x squared times the negative 8, negative 2x times the negative 8. And this is what I get, a new polynomial. Now I don't need to use the product rule because all I need to do is follow the addition and subtraction rule, the constant multiple rule, and the power rule, and I can take the derivative of this. So it becomes 12x cubed plus 6x squared minus 48x minus 16. So again, I just applied those rules that we already know. Now if I do the product rule, I have to take the derivative of the first expression, so my 3x squared plus 2x, the derivative of that is 6x plus 2, multiplied by the original second expression, x squared minus 8. Add because it's always addition in between these pieces with the product rule. Take the derivative of the second expression, 2x, times the original first expression, 3x squared plus 2x. Now I'll go ahead and FOIL out and distribute the 2x in, and I get 6x cubed plus 2x squared, blah, blah, blah. And when I combine like terms, hokey smokes, I've got the exact same answer as I did when I did the algebra first. Now, you're probably looking at this and you're going, well, you know, it looks easier if I do the algebra first. Well, this is with just a couple binomials multiplied together. You know, if you want to say, I don't want to do the product rule on these binomials, I'll just go ahead and FOIL and take the derivative. Hey, have at it. But there are times where you have to do this. You have to know how to take the product rule, because sometimes it's not just simple little polynomials multiplied together. Sometimes it's things that are more complicated, or they're things that you can't multiply together. So then you have to do the product rule. So you have to know how to do this. I just always use polynomials when introducing these rules, because we all feel very comfortable with polynomials. So let's take a look at something that we really could not get away from, the product rule. Even if I multiplied in this e to the r into my binomial, I would still have to apply the product rule. And I'd actually have to apply the product rule twice, because it would be r squared times e to the r, and it would be 2r times e to the r. So actually, I don't want to multiply this in, because now I would just have to use the product rule once. If I distributed it in, I'd have to apply that product rule twice. So let's go ahead and take a look at how to take this derivative. So I take the derivative of the first expression. The derivative of r squared plus 2r is 2r plus 2. Multiply it by the original second expression, e to the r. Plus, now when I take the derivative of the second expression, the derivative of e to the r, it is its own derivative. So g of x equals e to the r, g primed of x equals e to the r. This is the only function that this happens with, but it happens, and you know, it is its own derivative. Big whoop. Multiply it times the original first expression. And now, since I have the e to the r multiplying both of these binomials, what I think I'll do is go ahead and add these two binomials together. Now I'll combine like terms, and I have r squared plus 4r plus 2 times e to the r. And that's my derivative of r squared plus 2r times e to the r. Okay, now let's take a look at the quotient rule. This is a rule that we use basically whenever we see a fraction, or let me rephrase that, whenever we see a fraction that has variables on both the top and the bottom. If we see a fraction like x squared plus 4 over 2, I don't really need to use the quotient rule on that. I can actually treat that as a constant multiple, but I can use the quotient rule on it. So let's take a look at this. When I want to take the derivative of a quotient, when I want to take the derivative of a fraction, I've got some algebraic expression on top, f of x, some algebraic expression, g of x, on bottom. Here's my pattern. I take the original top function, I take the derivative, and I multiply it by the bottom. Minus, I take the original bottom expression, take the derivative, and that multiplies the original top expression. And then on the bottom we see the original bottom expression, g of x, is squared, multiplied by itself. So in this one, we can really mess this up if we don't pay attention to our pattern. Because it's minus there on the top of the fraction, that is not commutative. I could mix up the multiplication before the minus and after the minus and not be in trouble, but I can't mix up what's before the minus and what's after the minus. So really, you've got to practice this, you've got to get used to doing it, and you've got to get a good pattern developed so you don't mess this one up. Now, because it is so weird, and because the order does matter so much, I've got a little trick to help you remember it. So if I want to take the derivative of a fraction where it's high over ho. So high is just, a way to express my top expression, and ho is the lower one. And the reason I do this is because it sounds cool. So the derivative of high over ho is ho d high minus high d ho all over ho ho. A nice easy way to remember it. Ho-de hi minus hi-de ho all over ho-ho. Okay, so let's prove this quotient rule again. So I set it up with an expression on the top and an expression on the bottom where we can take the derivative of this using the power rule if I distribute that x first. So if I do the algebra first, I can avoid the quotient rule. So I don't always want to do this. Sometimes I can't do this. Sometimes it would be really difficult to do this. So this is one where we can avoid the quotient rule, but it's a good way to show that the quotient rule works. So if I go ahead and distribute that x to the x squared, the 2x, and the 4, this is what I get algebraically, x plus 2 minus 4 to the negative first power. All things that I can do just using the power rule, the constant rule, the addition and subtraction rule, all those rules that we've used before and we feel comfortable with. So the derivative becomes 1 plus 4x to the negative 2 power. Now obviously I'm going to do a little bit of algebra to this because I don't like that negative 2 power. And as a matter of fact, my general rule of thumb here is I try to give the answer in the same form that they gave the problem to me. So I want one big fraction. So I created a common denominator and I combined. So I have x squared plus 4 over x squared. Now when I apply the quotient rule, remember, ho-de hi. So ho is the bottom expression, not the derivative of it. So ho-de hi minus hi d ho. Well, where is d ho in this expression? Well, the derivative of the bottom, the derivative of x, is just 1. So I really didn't put it in there because multiplying by 1 doesn't really do anything for us. All over ho ho. So that means that I square the original bottom. Now I'm going to go ahead and distribute the x. Distribute this minus. Remember, this minus goes to all three of these terms. That's why you see the sign change throughout. I combine like terms, and hokey smokes Bullwinkle, I get x squared plus 4 over x squared again. So really just a way to show you that yes, the quotient rule does work. Now let's go ahead, take a look at one where I could not, or at least trying to divide out this bottom would be, ridiculously difficult. I mean, I'd have to probably multiply by a conjugate maybe. Whew. Let's just go ahead and use the quotient rule on this. Now, when I take the derivative of the top, when I take the derivative of the bottom, I'm going to have to take the derivative of a square root of x. Now, we've taken the derivative of the square root of x. We've used the power rule to do that. We've done this several times, and you can probably recognize now that the derivative of the square root of x is 1 over 2 square root of x. So I've got ho d hi minus hi d ho all over ho ho, all over the bottom squared. Now on the top you're looking at this and you're going, holy crap, I got little fractions on the top of this big fraction. Hey, they've already got a common denominator of 2 square root of x. Well, let's go ahead and just combine those fractions on top since they already have a common denominator. So I've got the square root of x minus 1 minus, now remember this minus gets distributed, so it's minus the square root of x minus 1. Those square roots of x cancel out, and what I'm going to have is a negative 2 on top over 2 square root of x. Those 2's cancel to 1's, and I'm going to go ahead and move that square root down to the bottom where it really belongs, and you'll see that square root of x right here in front. Whether you put it in front or put it in the back does not matter. Now this is calculus. This is a class where we're learning how to take the derivatives, we're learning how to do these new techniques. I am not going to ask you to rationalize the denominator or anything like that. They gave this problem to us with a square root in the bottom, so we're totally happy to have these square roots. So let's just leave our answer like that, and we'll move on with our lives and work on our next product rule or our next quotient rule. And actually, we're all done with this video, so this is time for you to work on those next product rule and quotient rule problems. So it's time to get to work. I'll see you in class, and I'll see you online.